that is geometric optics, or also known as ray optics, right? So in the last session, we have done that first part of the things, we can say, right? All the electrostatics, magnetic chapters we have completed. We have revised all of those. Right? So today's topic is geometric optics, in which we have the all reflection, refraction, lenses. So what is important in this chapter is all the derivations are important here, right? Then formulas we can say for, let's say, to find out the focal length or the image distance, object distance, or the refraction part is important. Plus a small concept we need to know about the, let's say, prism, then a simple microscope, telescope. Those things we are going to study today. Okay. So first thing is very simple. That is a reflection. So when we say reflection, we know that when the incident light falls on the reflecting surface like a mirror, this angle we can call it as angle I, or angle of incidence. And when it reflects back, we can call that angle as R. Right. So what to remember in this, the basic two laws of the reflection we can remember. That is, angle of incidence is equal to angle of reflection. Then second law is that incident ray, then the reflected ray, and the normal lie in the same plane, right? So that one extra thing you can remember in this reflection part. So simple basic question they can ask on this, that the angle, suppose sometimes they will give the angle the incident ray makes with the horizontal, right? Like for example, 30 degree is the angle, then what will be the reflection angle? So if this angle is 30 degree, then you can say angle I is 30. So angle I is 90 minus 30. That will be 60 degree. And if it is 60 degree, then you can say angle R is equal to also 60 degree. Okay. Then next part is the refraction. So refraction means what? When the incident beam passes from rarer to denser medium, or from denser to rarer medium. That time we can call it as a refraction. So for example, the light goes from, let's say, air to glass, or air to water, or other way around. Right? Can also go from glass to air or water to air, like that. So two different mediums are involved. In the reflection, there is only one medium. Right? So take the example of water. This we can call it as an incident ray. Again, that angle I as it is. After that, if the light is going from, let's say, rarer medium, so obviously now in this case the air will be the rarer medium. This will be the denser medium. Rarer medium means refractive index. So refractive index is the one property which we need to remember in this. So refractive index of rarer medium, let's say N1. For denser medium, it is N2. Right? So if the light is going from rarer to denser, we know that light bends towards the normal. That will be angle R. Right? And as I said, other way around is also possible. From the water or from the denser medium, the light goes into the rarer medium. Then what will happen? So again, you have the normal here. Light goes like this from here, and it will go like this, right? So this is angle I, this is angle R. We have this as a denser medium, refractive index N2. This is your rarer medium, refractive index N1, right? So both are these refraction, but we can see the difference between those two. In the first one, remember the ray bends towards the normal. Here I can say ray bends away from the normal. So in this case, angle I is greater than angle R. Here you can see angle I is less than angle R. Angle, let me write like this. I is less than R, and here I is greater than R. So what are the laws here? So here we have seen the two laws. One is angle, incident angle is reflected angle. And the second one is incident, reflected, normal, all lie in the same plane. In the refraction case also we have the two laws. First, one law is same, that normal incident ray, and another one is refracted ray. Yeah, incident ray, refracted ray, right? Here also I can call this as a refracted ray. So incident ray, normal, and the refracted ray lie in the same plane. That is the one law. Another law is a little bit different. And also called another law as Snell's law. It says that sine of the incident angle, or sine of the incident angle, or ratio of the sine of the incident angle to sine of the refraction angle is constant. That constant is equal to refractive index n. Refractive index of what? Refractive index of second medium with respect to first medium. What is the meaning of this? So ray started from the medium, so we can call this medium as first, right? So let's say this is the first medium, this one is the second medium. So in this particular case, what I can say, that the ray is going from n1 to n2, right? So I can also say this is n2 upon n1, right? Or simple, I can say n1 sin I is equal to n2 sin R. So this is about the refraction. So you should know the two laws for reflection, two laws for refraction. After that, there is one more concept, that is the apparent depth. So consider, again, we can take the example of water itself. Suppose there is an object here, any object, right? So we know that from this object, the rays will go towards all the directions, right? So here, now suppose this ray, can consider the ray going like this. It will go as it is. The ray which is going in this direction, it will go horizontally here, right? But suppose there is one ray which is going like this, making an incident angle I. After a refraction, it will go here. And suppose the person is standing here, this is the eye I have shown. Right? So this ray meets with the eye of the person, right? So I will remove all the other remaining waves. We don't need those. Okay. So now what the human eye think that the ray or light ray cannot bend, right? So human eye will think that this ray is actually coming from this point. Right? So human eye will think that object is actually here, right? So this we can call it as a apparent depth. This is called as apparent depth. Let's say HE, where actually the real depth, this is the real depth, HR. So we just need to remember one small formula between that. Or let's say this, if I call this as N water, this is N air, right? Then what we can say that sin I upon sin r, right? Sin I upon sin r. What do we know? Refractive index of second medium with respect to first medium, right? This is the formula. Or what do we know? N1 sin I is equal to N2 sin r. This one also I can use. Now, which one is N1 here? The N1 is not air. N1 is your water. This is the first medium. This one is the second medium, right? So if the N1 is water, I can say that is NW sin R is equal to, let's say, N air sin of R, right? So like this. Then suppose if I complete this triangle here as well as this triangle here, right? Let me name this as A, B, C, D, and E. So from this small triangle, so what I can say that this one is angle R, and if this one is angle R, this bigger angle you can see, this bigger angle is also R from that yellow triangle, right? So small derivation you can do here for the apparent depth. Apparent depth means our job is to find out that HA, that is our apparent depth, right? So let's see what will happen. So in this case, I can also say this is, first of all, let's find out the tan I and tan I can say. So tan I from this red triangle, you can say, right? So tan I is equal to what? It is equal to DE upon AE. Or let's say DE upon AE is nothing but your HR. Then let's similarly tan R from the yellow triangle. From the yellow triangle, what I can say, tan R is equal to BC upon AC, right? So, and also you can observe BC and DE are exactly equal. So instead of BC, I can also say it is a D divided by AC. Or that AC is nothing but your HA apparent. Like this. Now, one more concept we many times use in the physics, that if the angle is small, sin I, angle is small, sin I or sin theta is approximately equal to theta. Similarly, tan theta is approximately equal to theta. So what I can say, this NW into I, NA into R, but angle needs to be smaller for that. Here also I can say the same thing. This is nothing but tan I is equal to I. This one is your R. So just substitute this value of I here. So I can say NW into DE upon HR, means height or real depth, we can say, right? Is equal to NA. NA means what? Refractive index of air into R, DE upon HA. HA means what? Apparent depth. That's what we need to find out. So what will happen in this case? DE cancel, right? So we need to find out what? Let's say HA. So let's take the HA to the other side. Is equal to NA. Take the NW to the other side into HR. Simple, right? So this is another formula we can prepare for the apparent depth here, right? Simple. So this is a small derivation also you can remember, very easily it will give you some marks. Okay, so based on this you can try one question. Suppose in a container, if there is a water, and the refractive index of water is given as 4/3, and let's say the water is completely filled like this. The height of this water is 5 meters. Question will be, if the person is watching from the top, right, the base of the water or the apparent depth of the water will be how much? So that height will come here. We can say that is the apparent depth in this case. Right? So this will be your apparent depth HA. This will be your HR. Right? So we already know the formula. HA is equal to what? HA is equal to NA upon NW into HR. Right? Shall we do the quick calculation? Fast. Give me the answer. No. NA means it's a refractive index of air. This is the refractive index of air. N means refractive index, A means A for air. Okay, so this is 1 divided by 4/3 into real depth is 5, right? So you'll get this as 15 by 4, or how much is this? 3.75, right? So this will be 3.75, you can say. Now after that, we have the next point, that is the total internal reflection. Again, we will consider one, let's say, denser medium. So remember, it's not always be water, right? Could be anything. Let's take the glass this time. So for total internal reflection to happen, consider there is a, let's say, source here, light source in the inside the glass, you can say, right? So again, it will send the light in all the possible directions. So one will be like this, another will be like this. Now, first light will go as it is because it is, let's say, perpendicular to the surface. But the second light, after reflection, will become something like this. It will bend away from the normal because we are going from denser to rarer medium. Third light you can consider, if the angle of incidence is increased, what will happen? The angle of refraction will also increase. So this is your new I, this is your R. Consider the another light. As you can see, R is going on increasing at some particular value of incident angle I. The angle of refraction will become exactly 90 degrees. Means it will go along the glass surface, right? So that particular incident angle, we can call it as a critical angle. So this angle is critical angle. So incident angle, we will give the new name for that. That is a critical angle, right? And what will happen if you even increase the angle? Now it is more than IC. So this one is your angle, which is more than IC. So in this case, this ray will get reflected inside the glass itself, right? So therefore, it is called as a total internal reflection. So there is no mirror. There are two mediums. Still, we can see there is a reflection there, right? So to find out the IC means critical angle. What we know for this, let's say this ray. This is the ray, right? We'll show it by blue one. For this ray, we can say we are going to get the critical angle. So use the Snell's law for that, right? What you can say that n1 sin I is equal to n2 sin R. This is our formula. N1 means first medium. First medium in this case is we have taken glass, right? So let's say Ng, N for refractive index, G for glass. Sin IC, because that is our critical angle here. N2 means N air, sine of 90. We know that sine 90 is 1. This is Ng, sine of IC. Or sine of IC is equal to N of air, let's say, upon N of water. Sorry, glass. If I say that N of air is 1, we know the value of also, right? So if the first medium is air, I can say this is 1. The refractive index of glass, let's call it as N. So this is the formula or small derivation for critical angle, right? Critical angle in case of total internal reflection, right? So there are two conditions for total reflections or total internal reflection to happen. Write the conditions. So total internal reflection will happen only if first light must be going from denser to rarer medium. And second, now total internal reflection means this last ray you can see, right? That is getting totally internally reflected. So that is only possible if the angle of incidence is greater than critical angle, right? So possible. So angle of incidence must be greater than critical angle. Right? So according to this, there is one question also they can ask. This is very popular question, is something like this. In a water, suppose there is a water like this in a container, right? There is a light source here. And question says find the surface area through which light emerges. Okay. So there is another way to ask this question. They will say there is a fish here. Instead of light source, they will show. They will give that there is a fish there, and how much is the surface area that fish can see outside the water. Right? Concept for both of them is same, right? So remember the light, the straight light will go like this. It will not bend anywhere, right? Other light will go like this and it will bend, let's say like this. If the angle the light is going to make is, let's say, critical angle, I'll remove this ray. If this angle is critical angle, then light will not go outside. Means that only this much amount of, let's say, area is visible through that source, right? Same you can say here also. Here also the angle will be same, that is IC. The light will go like this along the surface. So only the area. Now in 2D it looks like this. In 3D it will be like a cone, or this top portion will be like a circular portion. Right? So they are asking the area, means if you can find out the radius, you can easily tell that that is a pi r square area. Right? So area will be pi r squared. They will provide you this one. This is given as 80 centimeter. And the refractive index of water, NW, refractive index is 4/8. So if this one is IC, our job is to find out the radius. Once we get the radius, it's easy, right? So radius means, let me remove this. So this is your radius. If this angle is IC, this is exactly means IC, right? Alternate interior angles, we can say. So let's call this triangle as A, B, and C. So what you can say from triangle ABC? Tan IC is equal to, tan IC is equal to what? Opposite, that is R upon H, right? Why H? H is this distance, that is 80 centimeter given, right? Or let me write like this: opposite is BC upon adjacent is AB. So BC is your R upon H. Now question is how to find out the tan IC. So if this is the water, we know this refractive index of that, right? So refractive index is 4/3. And we also know the formula here, sin IC. So sin IC is equal to what? Sin IC is 1/n. N of what? N of water. So this sin IC will become 3/4. So if the sin IC is 3/4, now your job is to find out the tan IC. Substitute that tan IC here. H is 80 centimeter. Find out the value of R. Right? Shall try this question. Tell me the answer of R. You don't have to calculate area. I know you can easily do that. Just give me the answer for R. Sorry. Sure. So from this, what you can do, once you know the sign IC, just create one small triangle there, right? So sign, if this one is IC, you can say opposite is 3, hypotenuse is 4. So using the Pythagoras, you can easily find out the value of this remaining side. That will be 16 minus 9, right? Root 7, you can easily find out the value. And then tan IC you can get opposite upon adjacent. 3 upon root 7. Substitute here. R you need to calculate. H is 80 centimeter means 0.8. So you'll get the R from here. Substitute the R here. You'll get the area, right? So this is the process you can solve this by. Right? Two types of question, either from the light question or the fish question they can ask. How much surface area fish can see, right? The same process you can use there also. Okay. Sure. So next. The next point is refraction by the spherical surface. Right. This is another important derivation you have in this chapter. Right. So suppose there is a curved surface. And this medium is a denser medium, right? Let me show that a bit bigger. And object is somewhere here. Now, this is a curved surface. Curved surface definitely will have, let's say, the center. Any curved surface, if you can draw the imaginary sphere to that, right? What you can say, there will be a center of curvature. So center of curvature, let's say here, right? So this distance will be like a radius of curvature, I can say. If I call this as a C, this will be like a radius of curvature, R. Suppose any ray from this object goes here, right? It is going to get refracted inside this medium. So first I will need the normal for that. So always remember, for the curved surface, right? For the curved surface, the normal always passes through the center of curvature, right? So I have to draw the line which is passing from this incident point as well as this center of curvature. Right? Then this angle will be I. Now the light is going from the rarer medium to the denser medium, so it will bend towards the normal. So it will go like this and meet the principal axis here. Right? So here the image I will be formed. Right? So I will call this angle. This one is your alpha. This one is your beta. This one is your gamma. Okay. If this point is N, then this point will be P. Right? Then, so P is for, let's say, pole. Even though there is a curvature, we are going to consider that ENP is a little bit straight line there. Okay. Now, so from P point, this distance is radius of curvature. This distance is object distance, right? So you can call it as an object distance. This U will be negative because we know the sign conventions from the pole. All the distances towards the left are negative, right? And this R will be positive. One more thing is there, that is a image distance. Let's say V. V is also positive here. So in this derivation, what you need to remember first is that alpha, beta, and gamma, right? We are going to need the relation between all of those. So if this one is I will say this one is angle R, right? Angle made after refraction by the refracted ray with the normal, that is R. Okay. Then what I can say, let's say triangle O, N, O, N, and C triangle I will take. So in this triangle, I can say that alpha plus gamma. This is your beta here. This is the gamma, right? Don't get confused with the gamma and the R. So alpha plus beta is equal to, alpha plus gamma is equal to R. Oh, not R, I. Why I? So focus on this triangle, O, N, and C triangle. And you can see that alpha and gamma are the internal angle of the triangle and I is the external angle. Right? So you can also call this as by external angle theorem. Right? Then consider another triangle, that is NC. We need gamma, beta, and R, right? So triangle, let's say NCI. In that triangle, angle R plus beta, I can say, is equal to your gamma. Or I can say beta or gamma minus beta is equal to R. the concept or reason is same. There is the external angle theorem, right? So first of all, find out the alpha, beta, gamma in terms of angle I and angle R. Angle I is our angle of incidence. Angle R is our angle of refraction, right? So after that, what you can say, N1 sin I. This is our Snell's law. N2 sin R, or N1 into I is equal to N2 into R. Reason, if angle is small, we can say sin theta is approximately equal to theta, right? So sin I, we can say it is I. Right? Now angle I is what? It is alpha plus gamma. So use that. So N1 into alpha plus gamma is equal to N2. For R, it is gamma minus beta. So it is N1 alpha plus N1 gamma is equal to N2 gamma minus N2 beta. Right? So after that, what we need to do, there are two terms of the gamma, bring them closer, right? And all other terms stick to the other side. So I can say this will become N1 alpha, bring this term to here, that will be N2 beta, right? Is equal to what? This is N2 gamma minus N1 gamma, right? Then, so this is N1 alpha plus N2 beta is equal to N2 minus N1 gamma. Now remember, our aim is to derive the relation. So always keep one eye on what we need to prove. So actually we need to prove something like this: N2 by V minus N1 by U is equal to N2 minus N1 upon R. This is what we need to prove, right? So you can see N1 alpha, N2 beta, and N2 minus N1. So all those terms already we have got here. V, U, and R we need to bring from somewhere. So for that, we are going to use the alpha equation, alpha, beta, gamma equation. So from triangle, let's say ONP triangle. Tan alpha approximately, I will say it is equal to alpha. Tan alpha approximately equal to alpha. Why? Because if the angle is small, we can say, right? Tan alpha is equal to NP upon that OP. Similarly, tan beta is approximately equal to beta is equal to what? Opposite beta. Beta is here. Opposite is NP upon this distance is PI. Then you have the tan gamma approximately equal to gamma. Gamma is NP upon R, right? Positive R. NP upon, let's say, PC. Now, this OP, if you think, OP is nothing but the object distance here, right? So object distance will be negative U, I can say. That will be NP upon negative U is equal to NP upon, for PI, P to I, right? We can say it is a positive V is equal to NP upon PC. PC is positive R. That's it. So use those alpha, beta, gamma here. Okay. So N1 into alpha plus N2 into beta. Beta is NP upon V is equal to N2 minus N1 into gamma. Gamma means NP upon R. Okay. Sure. So solve this one and let me know whether you get the same result which we need to prove this one. Okay. So let me know if there's any doubt here through this. Sure. So next problem, next derivation we have is a refraction by the lenses. So this is the curved surface. Only one curved surface was there, right? Now the second one. So I hope you got this one as n2 by v minus n1 by u, n2 minus n1 by right. This is the derivation. But make sure when you're doing this derivation, try to write some wording format in that, right? So explain the whole diagram in the words and everything, right? Then next one we have the refraction by lens or lens maker formula. So using the previous derivation, you can do that. You can also use, derive the lens maker formula. Lens maker formula means lens formula, which we already know. So what to prove here? To prove 1 by f is equal to 1 by v minus 1 by u. So when we talk about the lens, so this is the principal axis. So the object is here. Let's say the distance of the object is u, which is negative, obviously. And image will get somewhere, let's say here. This is the image. Let's say v. Now, as this is the lens is made up of two parts actually. So we can segregate the lens into two parts, right? So this is again the principal axis. So one part of this lens will be something like this, half part. So this is the half part, you can say, right? And another half part is like this. Let me show like this here. So first, if the object is kept here, so what will happen? The first part of this lens will create the image, let's say somewhere here. So initially, we can see that there are two curved surface. If there is a one curved surface, we already have seen, for one curved surface, there is a one imaginary spherical thingy which has the radius r. Now this lens has the two spherical surfaces. So what I can say that there will be two radius of curvature, right? So one circle will be something like this. So let's say this is a distance r. R is a radius of curvature. And let's say the first part creates the image at this place. So we can call this as V or V dash. This is not a final image, because this is only the half part we have considered. Right? Now in the second case, consider another half part we will consider here. So now the first part's image, that is I dash, will act as an object for the second part. Right? So I dash here, the distance from the center or the lens is V dash. Now that I dash, which was the image for the first part of the lens, will act as an object for the second part, right? So we can say the light will go like this, and this will be the final image now. So let's say I, or image distance is V. Again, if you draw the spherical thingy or imaginary sphere, we'll get the center of curvature somewhere here. And on this side, I can say this one will be the R2. So this is R2. Obviously, the first part we have is the R1. Right? So like this. Now we are going to use this formula. Now let's try to understand what this formula suggests. What are the different things they have written here? So when we say En2, N2 is the second medium or refractive index of second medium. We are going to use the same formula for these two parts to ultimately arrive at this relation, right? So these both derivations are important. They have asked this derivation in previous years also. N2 means refractive index of second medium. N1 is the refractive index of first medium. V is a image distance. U is the object distance. R is the radius of curvature. So for both the parts, we are going to use this one, right? And ultimately, this basic master formula we are going to use, right? So when we say second medium, here the first medium is air and another medium is of lens, right? So in the first case, there are two parts. In the first part, we can say the first medium is air and second medium is glass, right? What I can say in this case, that first medium, let's say air. So I will say that N1 is equal to Na, right? Here. Second medium is glass. So N2 is Ng. Then object distance. Object distance here is U. Right? Image distance. Image distance is V dash, not V. It is a V dash. That is a first image formed by the only half part, we can say, right? And radius is R or R1. So what I will do, I will substitute all these value in this basic formula, the previous derivation we have done. So N2, for N2, we have the N glass upon V. V is image distance. Our image distance is V dash minus. We have N1. N1 is Na. Object distance is U. N2 minus N1, right? So N2 minus N1 will give me Ng minus Na upon R1, right? Now what happens in the second part? Now remember, in the second part, the medium got exchanged, right? So in this case, the first medium is lens or glass, we can say. So N1 is your Ng in this case. Second medium is your air. So N2 is Na. Object distance. Now I dash is the image of the first part that is going to act as an image for the second part. So I dash is the object distance, that is V dash. And image distance is V. That is a final image, right? And radius, we can say it is a R2. So again, substitute in the master formula N2 upon V. N2 means second. Second is Na upon V. V means image distance, that is V. Then we have N1 upon U, right? N1 means first, let's say, medium, Ng upon object distance is V dash in this case, is equal to second minus first divided by R2. That's it. Once we got these two equations, you can just add both of them. Add first and second. This is equation number 1. This one is equation number 2. So if you add these two, what will happen? What you can get, this Ng minus V dash, right? The first term, this term, and this another term. You can say one is positive, one is negative. It will get cancelled. Here you will have Na Na upon U. Here you have Na upon V, right? So I'll write this one first because it is positive. So Na, refractive index of air upon V, minus refractive index of air upon U is equal to. We also have to add this one and this one, right? So Ng minus Na upon R1 plus NG minus NA upon R2, right? So here I'm going to do a small modification in this term. What I will say, this is NG minus NA R1, and instead of calling this as NG minus NA, I will say NA minus NG. So I just have to adjust that one small term, so that middle term, this term will become negative. So divided by R2. Something is wrong. This was initially NA minus NG, right? Now after changing this, this will become NG minus NA. So what is the benefit of that? You can see the numerator of both are same now. So this will become NG minus NA in bracket 1 upon R1 minus 1 upon R2. Here also, in this case also, I can take the NA outside. So this will become 1 upon V minus 1 by U, or 1 by V minus 1 by U is equal to this NA we will take to the other side. Like this. So this is the one equation we will get. Then what else we know? Here one condition we need to remember, which we already know. If object distance is infinity, then V is equal to focal length. Means if the object is kept at infinity, we do get the image at the focal length. So if you substitute these two values here in the previous step, what you will get? 1 by F minus 1 by infinity is equal to this. You can say NG upon NA minus 1 minus, sorry, 1 upon R1 minus 1 upon R2, right? Or 1 by F is equal to, this is nothing but, this is actually like this. If you remember, N21 is N2 upon N1, right? We can like this, right? Like this, right? So NGA upon NA, NG upon NA, we can say, sorry, NGA, we can say NG upon NA, or for simplification, let's keep it as N. Okay? So this you can write it as a N, because, or consider like this, the air's refractive index is 1. So as long as the first medium is air, we can directly write N. So N minus 1, 1 upon R1 minus 1 upon R2. Again, what you will say, this is equation number 1, this is equation number 2, and combine these two. From 1 and 2, you can say 1 by V minus 1 by U is equal to 1 by F. So this is another derivation. Do look bigger, but suppose consider these two derivations. This derivation and this two derivations are a little bit interconnected, right? So if you do one of them, you'll be able to do the another one easily. Right? And one more small extension to do to this one you can remember is the combined lenses, right? Or combined focal length. That is a small concept you can remember after this, right? So as I said, all the derivation, many derivations we have done in the reflection, the laws, refraction, the laws, apparent depth, small derivation, formula based question, then this light question, total internal reflection, this big derivation but important, and the lens maker's formula. This one is also important, right? And one small thing we will do, right, before stopping, that is a combined focal length. Means what? Suppose if you have the two lenses like this, right? So if you have the two lenses, first one has the focal length f1, another one has the focal length f2. Then the equivalent focal length, you can simply write as 1 upon EF equivalent is equal to 1 upon F1 plus 1 upon F2. One more thing you can remember is a power. Power of the combined power, you can say, or the basic formula for the power is P equivalent is equal to P1 plus P2. Why? Remember the powers formula, power is 1 by F. But the very important thing to notice in this powers formula is use the F in a meter. Because most of the times in the many numericals, focal length is mentioned in the centimeter. But if you are doing the calculation for the focal length, make sure that focal length is measured in the let's say meter, right? And one more small formula I can remember: if there is a gap between the two lenses, it's a gap of D. Again, the focal length is F1, F2, distance is D. Then 1 upon F equivalent, you can say it's 1 upon F1 plus 1 upon F2 minus D F1 into F2. Okay. This 2-3 small formulas also will give you the many marks, right? Or not many, but some marks you will get from that. Plus the basic questions like lens makers formula, object is kept here, where will be the image, what will be the nature of the image, inverted, erect, like that, right? So using the formula, you can easily get those answers also, right? Okay, so no problem. So these many derivations you can do from this chapter, plus some microscope, telescope, those derivations also you can try. So 2-3 derivations are there still. Prisms, one derivation you can try. So those some part you can obviously they will give you some marks, right? So no problem. I think we can stop here for today, guys. Thank you very much. Have a nice day. Bye bye.